Hello, everyone. This is Dwayne Matlack, and I'll be the moderator for the J2 Dam and Levee Breach Modeling and Risk Assessment track. Our first session will be estimating residential risk behind levees with breach modeling. It is being presented by Geoffrey Uhlemann with AECOM. He is a project manager for that group, and we will get started.
Good afternoon, and thanks for joining us virtually. I'm sure as many as you feel we would have loved to be with you in person, but at least the silver lining to this is you'll be able to rewatch this many times with family, friends, and loved ones. So whether you're watching from the basement, bathroom, or backyard, or back porch, sit back, relax, and prepare to be amazed as we talk about estimating residual risk behind levees with breach modeling. Now, since we can't be with you in person, we wanted to introduce ourselves briefly. I'll introduce myself first and then let Brad take over from here. But my name is Geoff Uhlemann. I'm a hydraulic engineer and project manager with AECOM. Been there about 12 years in Denver, and enjoy working on cool projects using math and science to serve great clients. I have 4 girls and a great wife, and we love to get out and go camping. So that's what we do in most of our spare time in Utah. So I'll let Brad introduce himself, and then he'll jump into our outline and kick off the first part of our presentation.
Thanks, Jeff. My name is Brad Winters, and I work with CDM Smith in Northern Virginia. I'm a water resources engineer working on FEMA projects. I'm also treasurer of the Virginia Floodplain Managers Association. And in a previous life, I worked at the Illinois Department of Natural Resources. As a silver lining, I was home for my 19th wedding anniversary this year instead of at the conference. So here's the outline. I'm going to discuss challenges, a few solutions, and then I'm going to pass it off to Jeff and take a deeper dive into methodology. And when I come back, I'm going to discuss about what a future case could look like. But as a note, neither of us work at FEMA. We're going to mention levee accreditation, but this is just so we can explain how the method looks compared to the current process. This is not a glimpse into the future. It's a glimpse into a future. Also notice the page numbers and the outline are in the lower left corner if you want to follow along at home. Okay, so most of us know accreditation. It's part of the hazard mapping procedure for specific levees that can meet specific rules. There's also the LAMP procedure, the analysis for and mapping procedure for non-accredited levees, and they're both very similar. They force levee owners to come up with data on their levees and face the realities of the hazard behind it at the 100 and 500 year and the interior drainage. But the maps are binary, whether you're in or out of the floodplain, and they don't take risks into account. And the LAMP procedure, it forces the modeler to make a choice on each of the reaches of the levee in order to map the hazard. The Corps also does risk analysis, from the most detailed quantitative risk analysis to modifying levee screening tool data that's less detailed. But these analysis don't take the flooding from local rainfall into account because they're focused on levee failure or overtopping during riverine flooding. So FEMA tries to message residual risk, they really do, but when the hazard is shown as binary or people aren't required to buy insurance, the general public could be lulled into a false sense of security, and some of them just decide they're not at risk. Or even worse, they believe this graphic somehow, hey, I helped my neighbor put up that fence, I know it's strong. If nothing else, they're lulled to not act because of the binary mapping. As shown here, the flooding at just deeper than the 100-year elevation, the property outside the regulated floodplain actually receives damage, and the one inside the floodplain does not. The current mapping also fails to show hazards during rarer storms over the 500-year that are becoming more common, and levee analysis is rarely updated except during a FEMA mapping project, regardless of the condition, hazard, or risk change in the intervening years. Okay, so assume my fantastic, amazing graphic here shows a 1% annual chance flood and an accredited levee. The houses on the right have the same hazard mapping in the current system, but does your gut say they have the same risk? Areas with the same mapped hazard shouldn't necessarily have the same risk. The one has flooding almost up to the eaves, and the other barely has flooding at all. But if you allow for graduating risk from most to least, each of these houses could have a different risk based on the hazards and the specific conditions of each structure. This would be more fair to each structure. Now, if we had a new house outside the mapped hazard, it should still have some risk based on a less frequent hazard, but we know that hazard could happen. No house has zero flood risk. It makes sense then that the solution that we propose for calculating risk behind levees would incorporate a graduated risk profile. Does the current system pass the gut test? Mine says not always. Accredited and non-accredited levees alike should have a graduated risk reduction, but based on their specific conditions. We need to catch the science up with our gut feelings. And now Jeff is looking at what that could look like.
All right, thanks Brad for laying the groundwork on how this is a need to address something new here. So I'd like to take a minute to look at what could a potential depiction of this look like. So again, as Brad mentioned, this isn't the answer. This is one potential way that you could do it. And these examples here, as you see, this is binary mapping. This is what we currently have today. But as Brad mentioned, we need to catch up the science with our intuition. So what might be some ways you can do that? So on the left-hand side, you can see there's different zones mapped there, and when it says X, shaded X protected by levee, so that's one zone, and then there's a defining line between another zone, but no other information in between. Now, if we were to display graduated hazard, you could display that in the form of an annual exceedance probability grid. And this here would show you where the risk or the hazard actually varies behind a levee within a zone. Similarly, we can look at risk or graduated risk in terms of what that hazard is against different structures. If you have structure information points that you want to assess that at, you can look at potential damages to assets using the metrics such as an average annualized loss or an AAL. So you can see on the right-hand side, within the same grid, you have all these individual points with varied degrees of damages within actually the same zone. So you have additional information that you can make decisions off of. Now, before we jump into a process or a methodology on how you could develop that information, I want to look at maybe a case study, we'll call it, where here we have an example for a levee. You can see the streams in magenta where it floods frequently. And so we're going to display graduated risk behind, or graduated hazard behind this levee. Now, under an accredited levee, under today's term, we would have just one zone that says that it's protected by levee, but there'd be no hazard information behind it. Now, if it weren't accredited, let's say it failed to meet, 446510, it would show complete risk or hazard behind it, no mitigation. And this could be just due to logistical requirements, such as not having documented regular inspections or not having a current emergency action plan. And that's the difference between what we're calling full protection versus no protection at all. Yet in reality, we know there's some degree of risk or hazard mitigation that's taking place. So if we were to look at this more from a graduated hazard and a risk reduction, that would allow us to move away from the overconfidence of accreditation and the ultra-conservative condition of natural valley. So perhaps you have a levee that doesn't meet what would typically be accredited, and it's in poor condition, so you do show a rather high hazard behind it, but it's still mitigated, such as shown in this example here. And in this example, maybe it does meet accreditation standards, but we're still acknowledging that there is some degree of hazard that's still present because it's not full protection, rather it's hazard mitigation or reduced hazard. So this methodology would allow for a spectrum of hazard reduction rather than just two sides, two extremes. And this would enable communities and decision makers to inform improvements along the levee where they could reduce hazard even further, or planning behind the levee where there is some hazard that they need to plan around. And also want to point out that this methodology then could be used for any type of feature. It doesn't have to just be a levee. You could do this for railroads or highways or berms. And we know that when we look at 1D modeling, those are often treated as not placing an ineffective but allowing effective flow behind, whereas in 2D modeling, often modelers will just put a brake line on top and you're really giving it full protection in a way. So this here would recognize a middle ground of risk reduction. So as you're getting the sense of AEP or annual exceedance probability grids are pretty crucial to this step, or one way of showing graduated hazard. So I wanted to go through a simplified illustration on how it's generated. So on the left, we'll pretend that this is a simple square mesh or grid in a model, and that when cells are wetted, we take those and we store that information in a raster with a system of ones. Now in reality, we'd multiply it by the event weight, but for purpose of illustration, we'll just accrue ones. So for purpose of this illustration, we'll show 4 events. So 4 different floodplains, and they're each aggregated, adding up. And you can see on the right here, some are 1s, 2s, and 3s, 4s. And if we then symbolize based on that, we can show graduated risk or graduated hazard along this floodplain to show the areas that are higher hazard versus lower hazard. Now, looking at what this might look like in a real-world example, we do the same process but with rasters. However, instead of using the value from the water surface elevation raster or depth raster, we just use the fact that there is a value as an indication of a wetted cell. So it's basically a 1 or a 0. Then we join that with the weight that's associated with that particular event for that raster, and then we aggregate all of that to an annual exceedance probability grid. So that's kind of in a nutshell how you generate AEP grids. Now I want to give kind of a quick crash course in how do we get this information. Graduated hazard and graduated risk are kind of core to how you can assess information behind levees. So how do you do that? So this slide's going to go over how that process is generated. How do you get this sort of information that can be used for those sort of outputs? So essentially, it's kind of like a modified Monte Carlo analysis. There's a way of sampling that we're calling importance sampling that enables you to sample across a very wide spectrum, but without having to sample thousands and thousands of times or sample randomly. Instead, you have prescribed sampled intervals and you assign different weights to them based on the relative portion of that sample set that it's representing. So if you're sampling between the 2-year and your 3,000 year, your 2 year is going to have a much greater weight, and your 3,000 year is going to have a very small weight. But that way you're not modeling your 2 year 1,500 times more frequently than you are your 3,000 year. And this allows you to get a good resolution without crazy amounts of sampling. So on the top here you see fluvial or riverine. So we're sampling between the 5% and the 95% confidence limit, not just along the median. And we're sampling across a wide range of events. On the lower part, pluvial or rainfall, we're sampling across different depths, different durations, quartiles and deciles of different distributions. All that information gets paired to be inputs into the hydraulic models. So on the top part there, those peak discharges from the log Pearson analysis are then paired with hydrographs that are based on historic events. And we have the inflow hydrographs then for a riverine analysis. And then on the bottom, you see an excess precip hyetograph. and that's based on pairing the applied precipits across all the different depths and distributions and durations. All that information, once we put it into the models, goes through the cloud, because there's, for riverine, for example, we did anywhere between 100 to 300, and for pluvial, we did near 1,000 on average. That information that gets aggregated into AEP grids, as we discussed before, but you can also do the same with risk, which I'll cover later in terms of damages, and get an average annualized loss. And you could even do this information with depth if you wanted to as well, to create an average annualized depth raster. So again, we just covered kind of in a nutshell how you would get graduated hazard information, and that's irrespective of whether an area is levied or not. So I wanted to briefly cover here, or summarize on this slide, what are the additional steps that you'd have to do for a levied area. So, and we'll go into each one of these, but kind of high level, you have to identify your breach locations, and once you have those located, you can determine parameters and erosion rates to get assigned to those locations. We then trigger different breaches that are dynamic breaching within the RAS model, and output the max water surface elevation. We pair this information with fragility curves to calculate the event weights, and then all of that gets used to calculate damages. And basically what we do is for every single event, it gets its own damage that's calculated associated with it, and then it has a probability applied to that. So a very large damage, a very small probability, and then it gets aggregated across all of the events. So as for breach locations, how do you decide where to put these? The first indicator is if there's been any past or historic breaches before, we would model a location there. Our next source of information is often looking to the Corps if they have inspection, or the levee owner if they have inspection reports, and we look for areas that have maybe compromised stability or any leakage. And then we also look in the model and see where are areas with lower freeboard, where are there sharp bends or high velocities, and that's where we would put breaches, and then we space them evenly to make sure that we also have complete coverage. So then once we have those, we modify the model, and we do this by putting in an internal connection, and then you can use the breach plan, and in doing so, this will actually allow you to breach across the terrain without modifying the terrain. And what it's essentially doing is it's acting as a weir, transferring water from one cell to the next one, and it dynamically widens and deepens or lowers the weir elevation based on the velocities that are being modeled on the river side of it. So when you're actually simulating these, we set erosion parameters based on the composition of the levee and any other information that we would be provided with. And you can see here on the lower left, this is a specific location that it widens at a different time step. So it's here it is on the left at 280 feet, and then later on at 140 feet wider, and you can see greater velocities going through it. And this makes a big difference what you choose. We did a sensitivity test here. These are the same inflow hydrograph applied to the model, and then same time step, but we used a high erosion rate shown in red, and a pink one that's representative of silt, and then a clay that's representative of black, and then green's kind of a mix of clay and others. But you can see the lateral extent and the associated depth is very different depending on what you put in terms of erosion parameters. Now, if you have a sufficiently long inflow hydrograph, it may not matter if we're talking weeks, but if you're talking days or hours, it will affect the results, and it's something that should be looked into. And again, the end output here is we export the maximum water surface elevations, and from this we can aggregate the information that we need. Now, so if you remember, I mentioned that we take the individual values, we calculate specific event damages, and then we pair that with probabilities. So we get those probabilities from the fragility curves, and the fragility curves are formed based on failure modes and any information that we have about levee composition, stability, etc. So these are some examples here shown, and erosion parameters and factors that you'd consider. All of that gets used to build a fragility curve. And essentially what the fragility curve is, it depends on the elevation, the river water surface elevation applied to the levee in terms of between the toe and the crest, and then it has a relative probability of failure. So in this example here, once you have that information, and again, that's independent of your results, you then apply your intact or your non-breaching results to those values. So in this example, if we were to model, let's just call this a 10-year event, we would model a 10-year breach, and then we would take the 10-year value from the non-breach or the intact and calculate what is the likelihood that that would have happened. And we'll say in this example, it's 2%. So then we would calculate the damages from the breach and apply a 2% probability to that. And then we would calculate the damages from the non-breaching or intact, which in this case would be nothing behind the levee, and give that a 98% weighting. And so then you can aggregate them. You can see as the water rises, it moves further along the curve, it becomes more likely. So in this example, you have a 12% likelihood of breaching and an 88% likelihood of intact, and that's how you would aggregate. So kind of summarizing how this would work out, because we've been mostly talking about AEP and graduated hazard, when this comes to risk calculation, you have the water surface elevation grids, and then you intersect that with your structure points. So let's use just one building as an example. You would extract it from all the rasters. So let's say we're doing 300 events, and you would create a flood elevation curve where each of those would be 300 different points that are connected at that single location. And from that flood elevation curve, you would then apply your depth damage functions based on the structure type and the property values and deductible, any sort of information that go into the risk assessment calculations, and you would convert your flood elevation curve to the flood damage curve. And then the average annualized loss is essentially the area under the curve, and you can do that through just taking different weights associated with each of those slices. You can basically put it into different slices, and for each one, like we looked at for the fragility curve, give it a likelihood of occurring and take that individual damage and multiply it by a weight. So that's kind of a quick overview of how do you get here? What's that methodology look like? And now I want to consider what would we submit and why does that matter? So in today's paradigm, often when you do a study or a LOMAR, the end product is here's the new floodplains, here's the new zone that goes behind it. And this is important because of building codes and compliance and it affects insurance rates. And the reason why you want to do that is because if you don't, you're stuck with natural valley. Now, what might this look like for a future option? We don't know exactly what that could look like or what that would, but we do know one option, and that would be maybe a letter of risk revision or hazard revision or whatever you want to call it. But the end product there is updated grids and AAL, so you give updated graduated hazard information and graduated risk information. And this can be used to inform planning and decision making and investments, and it would similarly affect your insurance premiums as well, but it would be tied to hazard, not a zone. And then you're incentivizing people because they can actually directly correlate an improvement with the cost savings. So again, this is what it could look like, and I'm going to turn it back to Brad, and he's going to look through and give a couple real world examples of how this could play out.
Thanks, Jeff. So here's a couple of examples. The one on the left is a well-maintained, good height levee. The one on the right is a dredge line, most likely spoil pile that has a woodland growing over the top of it, old sandbags, garbage, and is generally poor condition. So regardless of what the levee is or the levee parameters are, the same analysis is used to determine the risk behind these levees. Assuming that we're going to do a risk behind this levee on the right. But we could. And we can use known parameters as a factor to correlate. If there are unknown factors, we could set those on the very poor side of that factor's range. That way, the fragility curves would show the actual risk of the unknown parameter. But the the risk behind the known levee, where the parameters are known, would show a lower risk because the factors behind it are known and it has a lower risk behind it, as it should be. So here's some of the parameters that could affect fragility curves. Does the levee have a sponsor? Do they have an O&M, an emergency action plan? Is regular maintenance completed and recorded? Is there structural design and is it accurate? Do they perform regular inspections and record them? Does the levee perform well during historic loadings? Is there detailed foundation data? What is the levee composition? And what is the levee top and toe elevations? You can see the parameters that affect the hydraulic modeling are in blue. So the one in orange are applied after the hydraulic modeling is totally complete. And levee composition in blue might not matter either if it's a long duration flood watershed where there's time for the leveed area to fill regardless of the soil type and breach width. So in this example, from a poor embankment on the red line, the estimated likelihood of failure at 70% of the levee height shown along the bottom axis is 70% along the left side. And an average embankment on the yellow line is 17% at the same levee height. So the reduction in estimated risk of failure is 53% by just changing the fragility curve. Now we can update information about levees without updating hydraulics, since the fragility curve is done afterwards. It'd be very quick and easy to update the risk behind the levee by updating the parameters of the fragility curve and redoing the risk analysis. Levee owners can run sensitivity analysis on levee maintenance and upgrades to determine what changes give the most risk reduction without having to rerun complicated hydraulics. Completing regular inspections and maintenance records, they could remove encroachments or unwanted vegetation, they could create O&M or emergency action plan, or record loading events and their effects. When they do these type of activities, it could lower the fragility curve because they reduce their risk. And when the fragility curve is lowered, the multipliers are lowered, so there's less risk calculated in the AEP and damage grid because there's a smaller likelihood of levee failure. With this procedure, the levee owners have the ultimate responsibility for their levee to show and keep up the risk reduction behind their levees. If all they have is basic data needed for the breach modeling, all of their data could be gathered later and it could just penalize their fragility curve. If they don't know the data or have poor data, they're going to show much higher risk. It's just like auto insurance. If you don't have accidents or tickets and you use one of those monitoring device plugs, you're a known risk and you can get cheaper insurance. But if you have a history of poor performance or you're a higher risk, they charge you more. But it's up to you to make the changes to reduce your own risk. You're in the driver's seat. So when moving away from binary mapping to graduated risk analysis, the same process for the hydraulic modeling is used for each and every levee. Partial credits provided for levees and non-levee features. It's not an all or nothing thing. And this addresses the misconceptions of levees providing absolute protection, because it quantifies the risk behind levees in financial terms. That also incentivizes levee owners to decrease the risk behind their levees because the risk is quantified.
Hello, everyone. That is the end of our presentation. We'll now be going into the question and answer portion of the session. We have several questions that were asked. The first question is, the Army Corps of Engineers has mapped residential risk behind levees in some regions of the U.S., but these maps are not available for the general public. How does the approach that you propose differ from the Corps' approach?
I'll take that one, Dwayne. Yeah, thanks for the question. It's very similar to the core approach. We modified it a little bit. We used importance sampling for our Monte Carlo approach. Also, we used rain on grid behind the levee, as well as the riverine flooding like the core was doing. So we have both of those hazards in our analysis type.
I'll just add one more thing on kind of the end use. Usually the core is looking at it from estimated damages and then also considering life loss, where this is more focused on average annualized loss. So similar metrics, but a little different focus.
Thank you for the answers. The next question that we have is, do you know if any city, county that uses these maps to manage flood risk?
I'll answer that one. I'll actually answer it in accordance with the other question too about risk rating 2.0. They're somewhat related in that regard. So this is a newer methodology that was developed maybe starting about 1.5 years ago and has continued to develop. So it is fairly new in the sense that not many counties or cities have looked at it. I know of maybe one instance where it's been used to evaluate whether it made sense to move forward and accredit a levee. So we showed them actual risk with that information. But beyond that, it is kind of a newer approach that was used in association to help support risk rating 2.0. And I guess I would just encourage people to look back at last year's ASFPM presentation. Andy Neal had one where he talked about sausage, and it was CAT models, mapping data integration, which is basically the effective data, and then this probabilistic approach was one piece of the data that was considered as they were developing an approach for risk rating.
Thanks, Jeff. The last question that we had, and it's really not that much of a question, but we have a question that asks, are the presentations available from ASFPM?
Yes, and it looks like one other question came in too.
Yeah, I see that they just came in. Another question, shouldn't levee height also be considered regardless of if it is accredited and maintained? If there is a 20-foot differential behind the levee, it seems like the risk factor should still be high regardless of the levee condition.
Right. So for the levee factor, in terms of where the height comes in, it does play into the breach width, but its main component is when it comes into levee loading. So however much what your water surface elevation is on the river side of that. So in terms of a fragility curve, that is unitless. But in terms of when you apply it to your probabilities by looking at your intact or your non-breaching results, that is where, in terms of the water surface elevation relative to your height will play a factor in the calculations.
Hey, Jeff, can I add also the fragility curve is calculated based on those differences in elevation between the levee toe and the levee crest. So that elevation, those elevations are baked into the fragility curve.
And if we have time for one more question, did you estimate damage on the dry side of the levee using an estimate of the volume of water passing through the breach over the event duration? Or is the dry side assumed to flood entirely to a specific BFE?
So it is volumetrically driven. So it's an unsteady flow, and it's actually a dynamic breach that's happening during the model. So the breach itself will widen. So depending on the water surface elevation and the velocity adjacent to the breach, it'll actually regulate how much flow does enter the breach. So it's not a steady state.
Great, thank you. And that is the last question for that. Thanks, Jeff and Brad. Great presentation.
Thank you.
Moving on to the second presentation that we have will be the Sacramento County OES Flood Decision Support System, being presented by Chris Ferrari, and he is with GEI Consultants. Chris?
Thank you very much. Hello, my name is Chris Ferrari with GI Consultants, and I'm here to present a web-based tool for emergency managers in Sacramento, California. The participants in this tool was Sacramento County Office of Emergency Services, the state of California, Water Resources, National Weather Service, California Nevada River Forecast Center, and Reclamation Districts who will benefit from this tool. And future participants, as we expand the tool, will be Contra Costa, San Joaquin, Solano, and Yolo counties. These counties border Sacramento County in the area. So the Sacramento County received a grant in 2018 to develop a web-based tool, and this was after a pilot study was done, and a lot of this was based on after the Oroville event of the spillway failure in 2017. And one of the brainstorming parts of this whole program was, how do we find information quickly? I mean, there was, I wouldn't say unorganized, but the, trying to find maps, evacuation routes, what is happening with the rivers. We do have a forecasting program, but just to try to better understand how to gain access to information quickly. And that's what this program is about. It's a web-based tool to be able to at least direct decision makers in making decisions on just to understand how could you gain access to levee locations, emergency management type things. So that's what the goal is, to improve communications. It says within the Delta, but anywhere in the county, this could be used for a lot of different situations. The web-based tool is not intended for the public, so you need a username and password. It's used in the office, the field, the laptop, and tablet. What we tried to do is include just the essential information. Try not to overload too much information. There is a lot, but with training, you should be able to, the way it's organized, be able to find the information pretty quickly. And one of the things is we have it, the cross-section information connected to the River Forecast Center. So you'll be able to look at flow and stage data. And then also with this, you should be able to collect historical data if you're out in the field, get field photos, high watermarks that can be collected and used for future calibration or hydraulic model evaluation. One of the things I wanted to discuss is just the size of the watershed here, what Sacramento County is dealing with. A lot of the flows of the watershed are regulated. So you have major reservoirs, Shasta, Oroville, Bullard Bar, Campfire West, Folsom. All these regulate the flows coming into Sacramento County. That drains from north to south. Other areas, San Joaquin County or San Joaquin River watershed has a lot of different reservoirs that regulates the flows. The one river, the longest river that's unregulated in California, the Cosumnes River, which is shown in green here, produces a lot of flow and a lot of volume, and it does impact a lot of residents in the lower area. Then also you have tidal conditions from San Francisco Bay that also come together and can impact this area of the lower delta. So just my last slide before I get into the tool, some delta facts. You can see here in the red boundary, this is the area that it has, the size of California is 164,000 square miles. The watershed that drains to this area that's bounded in red here is about 26% of the area of California. So it's about 43,000 square miles drains either from the north or to the south through this area, through San Francisco, and it outlets into the bay. There's a lot of levees, a lot of farmland, a lot of rivers, a lot of habitat, and it also supplies water for millions of Californians throughout the Central Valley and California, down in even provided to the LA area. So my next presentation will be the actual tool for the development. Hello, phase 2 of my presentation is the actual tool that was developed for Sacramento County. So as discussed before, there's a username and password that is used before you sign in. So when you sign into the tool, you get, actually have a view of Sacramento County here. The county, I'll zoom out. Here's California. As you zoom in, like I showed before, here's San Francisco, Sacramento. And like I said, is we're really focusing on Sacramento County, which you can see is outlined in this area. Here's the Folsom Reservoir, here's the American River, and here's the Sacramento River. I'll just quickly turn on levee information so you could actually see the project, how many levees. Here's the project levees in the area. So you can actually see in red how many miles. There's about a little over, I'd say, 1,000 miles of project levee, which is maintained by the state and federal government. You can see in red, and then the non-project levees are areas that in yellow that are highlighted. You can actually see how many levees are maintained by local agencies in Sacramento. So I'll turn those off and I'll start from the incident command. So you have basically, you have incident command, communications, planning, logistics, operations, mapping, and evacuation and recovery. We try to organize the data in a way that seems logical and be able to access information quickly. So incidents really is if you're in the field and you want to report an incident to the base station, which right now is housed at Sacramento County. You basically would, if you're in an area, say for instance, downtown Sacramento, just pick an area that potentially can be impacted. You see the area in circle, sort of, it's a 2-mile diameter here area. What you would do is you'd report, you could say flood. And you would put in your name, description, you can call that flood. And you would have number, see your locations. You can decide what critical facilities you're really worried about, bridges, hospitals, floodgates in the area, schools. And then you can read, and if you know if there's an incident, you can look at the type of levee break. You can submit that incident and it will go to the base station. It would notify Sacramento County or whoever's in charge of there's an incident potentially at that location. If you want to view the critical facilities that you prepared, you can actually see that. You can see there how many schools, how many bridges in the area. That would be something you can do numerous things. You can do oil and gas pump stations, just whatever you need to show in the area, you can do that. That's really what the incident command tab is for, is to report incidents in the area. If you do want to know how much population you need to deal with, you can hit the population drawing module. You can actually estimate the area that you want to evacuate, hit demographics, and you can see in this area, 2 miles diameter, you can see about 45,000 people live in the area. So you can estimate quickly how many people that potentially would need to be evacuated in the area. So in that, then if you go to communications tab, is anything to do with communications. You could have consultants, you can have county contacts, you have federal contacts. The ICS chart is not live at this time, but you can actually have who's in charge of the incident command, the public officer, operations, planning, logistics. Depending on how big of the event is, you can actually, that will be live and you can populate names in the area. The reclamation districts, which is down in the Delta area, you'd have contacts for all those. There's an impact with all the levees and all the state contacts. So there's the communication is basically a Rolodex of information that would be accessed. Planning is all the essential information just for a planner to understand where FEMA information is, levee information, topographic information, watersheds. So you can actually bring up an earthquake. There's actually an earthquake zone in the area. If there's an earthquake, you can see the meridian fault. You can click on that and the information will come up. Critical facilities, airports, bridges, school, hospitals. You can get all those locations. Oil, gas pipelines, wells, you can see, you can populate this with anything you want. If you need to know what the gas line is, you can turn that on and it would tell you who owns that. It's a natural gas line. Fire stations in the area, if there's any, you could see there's a couple of fire stations here in Walnut Grove. Reclamation districts information, you can bring up emergency action plans, safety plans with that here. Topographic information, if you wanted to bring up Sacramento County, the city of Sac, you can actually draw cross sections on the fly if needed. Draw a cross section through there and actually give you a representation through an island if needed. You can see how low the island is, what the elevation is. You can see here's the river, here's the levee, and you can see the actual island is below zero elevation. So in this area, tidal can come up to 7 and 8 at some times. So you can see these levees are impacted several times in the year. There's terrain information, top of levee information. So you can layer control on the right. You can actually turn off the terrain if needed. And then if you wanted to look at watersheds, you can do that. Sub-watersheds, large watersheds, if there's need information, you can click on, what watershed this is in this area. So this would come up with a table and you can actually see what watershed. This one is basically this Beaver Lake, Sacramento River watershed. If there's need information, know where your watershed is. You go to the logistics tab. This is where all the inventory of materials is. You can bring up material locations, which you'll see here in Twitchell Island. There's a lot of storage for different areas. Gives the names, numbers, locations. Actually, Delta equipment. You can see that on the fly, and that helps with understanding who has equipment and where it's at. Operations is really what we're thinking under this is how's the system operate? How's the river system operate? How's it connected to to the River Forecast Center. So you pop up cross sections. So here's Folsom Reservoir. It releases water through the area. So you can bring up levee information. Here's project levees. So you can actually see there's levees surrounding about, I would say, 500,000 people live in this area behind levees, north and south of the American River, Sacramento. In this area, you could pick a cross section on the fly. Pick a cross section. Here's the cross section for that area. This is actually surveyed, LIDAR and bathymetry. You can enter a flow. 115,000 CFS is actually the 100-year flow release from the American River. You can see that it's up on the levees at 115,000. The capacity is about 160,000 CFS. You can see that's right at the top of the levee. That's about capacity of the river. If you want to look at the River Forecast Center, you actually click on the River Forecast. And in this area, you can see monitor stage at 39, 42, and 43 is danger stage. That's basically top of levee. And in this area, you can see nothing's happening right now. It's at elevation 16, so very low flow at this point. So some of the other tabs that actually, that's operations. We actually have travel times. You actually can view also review profiles. So you can see here's the American River profile, and you can actually turn on and off, say 115,000. You can actually see here's the water service profile for that area. You can see the high water marks in 1997, and see here you can actually see elevations from the levee if you want to see different elevations, top of levee, freeboard, if it's important, depending on what's happening at the time, you can actually view that. So that is available for all the major rivers in the watershed, profiles, cross sections throughout the area, depending on what your needs are. You can access cross sections and water service profiles and capacities throughout the Sacramento River system. So mapping and evacuation, that's really geared towards flood animations. City of Sacramento there's different levees and breach locations. You can see here, if you want to bring up flood extents, max flood depths, in an impacted area. This is Natomas, so you can turn on and off those and access flood data. Down here in the Cosumnes River, which I said earlier that's an unregulated river, you can actually bring up what was the major flood. The last major flood was 1997. You can actually see what the inundation is. Basically, this was modeled and calibrated with best available information. You can see what that impact was in this area. So there is residents that live in this area. There's a prison. There's an airport. So there's an area of quite a bit of levee in this area. So you can see the amount of backwater that occurred before it goes actually into the bay, which is down here. And you can see San Francisco, and all this is basically tidal conditions, but this area drains through rivers, McCollum River down into the bay, into the Pacific Ocean. The last thing I will show you is recovery. So what recovery is, if a levee was to fail and flood one of the islands, what we try to do at this point is estimate how long would it actually take to drain the island if that would occur. This did occur in what they would call Jones Track in this area. in 2004. So if a levee was to fail, you click on this and we'll just go to pick an island. Here's Grand Island. We put the pump locations basically at the lowest portion of the levee. So if you were to click on that, we'll just pick one. You can see we picked an area. We added the rating curves, what the top of levee, what the basin would be. And this is actually a highly populated area, Walnut Grove area. So you can actually, if you wanted to draw a cross section through there, you can actually do that on the fly to understand what the terrain is. You can see, here's the river, here's the terrain. You can see how much lower it's down in the well below sea level in this area. And in this area, you can actually look at breach information. So after like 4 hours, you can click on a breach. You can see how much inundation would occur in 8 hours if that was to fill in this location up on the Sacramento River. And then also here's the pump rating curves. So what we're trying to accomplish here is if a levee was to fail and you know how deep it is, you can actually estimate if you add 300 CFS pumps, it would take several days or weeks to pump out the water. Some of these islands are very large and it would take months. So if we look at a much larger island, this is Grand Island. And this is probably one of the larger islands in the area. Depending how deep it is, it could take 4, 5, 6 months, depending on, these are 600 CFS pumps, very large pump system. And you can see how long it would take, depending on how much the area flooded. So anyway, that just gives us an estimate on if the area was to flood, how much time it would take to pump out the system. That's the end of my presentation. I'll be happy to answer any questions. That's just a general overview of the area, but feel free to ask any questions. And thank you for listening to my presentation.
Hello, everyone. That is the end of this session. We'll now be going into the question and answer portion. We do have some questions here that Chris will attempt to answer. First question, Chris, is this a public tool?
No, it's not to the public. A lot of the information, like the flood mapping, can be made available to the public, but there's a lot of sensitive information in here. So it's really for emergency managers, for DWR, the Department of Water Resources, some local agencies. That's what we're trying to keep it to. It's just because of some of the sensitive data that's included in the tool.
Thanks. You mentioned that the tool was built in response to a disaster and needing a better system. Have you since used it during a disaster, and how did it perform?
Okay, so really this came about in my discussion from 2017, February, the Oroville event with the spillway, when the spillway collapsed, and luckily no one was hurt. But I do a lot of work with coordination with Sacramento County, and there was a lot of questions for forecasting, inundation mapping, evacuation routes, and that's how this all came about. A lot of this information is in GIS, and we decided, hey, what a better way to allow people that don't have access to GIS to go to a web-based type tool with the username and password so they can look at some of this information that's tied to the California Nevada River Forecast Center, hydraulic modeling that's been done in the past, and then also inundation mapping that, previous inundation mapping that we could pull into a web-based tool and let people have access to. And then as far as using that in other disasters, since 17, luckily Sacramento we've had high water where we've tested it, look at high water marks, but we haven't had that disaster. We're always preparing for that disaster. And that's, through tabletop exercises, that's how we improve what's actually in the tool, how we present it.
Thanks, Chris. Another question, how is the information updated and kept current?
That's a very good question. Right now, we're using the best available that's out there. And, our coordination with other counties and agencies, we're hoping that every year they can look at the contact names and numbers. So they would just go onto to the tool and be able to view it. If there's name changes, then they would notify us, GEI, or the Sacramento County, or the Department of Water Resources. And actually, it's once the tool is fully developed, probably at the end of this year, then DWR, the Department of Water Resources, is going to be housing the tool. So there's going to be a lot of coordination to keep that going, and with the 5 counties that's included in the Delta.
Thanks. Chris, next question. Do you have data for cities such as West Sacramento where there are no FEMA maps available?
So that's a very good question. So, that goes back to using best available information. I know a lot of the inundation maps, levee inundation maps, the city of Sacramento and the city of West Sacramento, which is in Yolo County, is available. And we are coordinating with Yolo County to include those into the tool. So we are coordinating and trying to get best available maps to include in the tool. Long as it's in a shapefile format, we have it set up so those are pretty easy to include into the tool now.
Thanks, Chris. For the emergency response function, is there an app, or do the responders have tablets or PCs?
Actually, out in the field, we've tested it a number of times with tablets, and just due to be able to see, I've tried to use it on a phone. It doesn't quite work as well as on a phone, but there is an app that I recommend others to use. It's called Theodolite. And what that can do, if you're in a disaster, you could take a picture and record your coordinates. And we're including, it's actually included in the tool. Someone can send a picture, and then they can update with the button, and it comes up and it shows the location potential impact, in the impact area that somebody can actually communicate if they don't have a tablet with them. So they can just take a picture, send it, the coordinates are recorded, and then that gets notifies somebody with the tablet or at a base station, whatever county, to that there's an issue going on at a certain point in the at that location in the Delta.
Nice. Do have a question here that says, any idea when other counties would be coming online with a similar app? Or
okay, so this all started out as a pilot study after I talked about the 17 event. We are coordinating with other counties. We're really focusing on what we call the Delta. If you're not familiar with that, that's the area between the Pacific Ocean and Sacramento or San Francisco and Sacramento area, where there's actually 5 counties that we're in discussions with to include other information. So right now we did focus on Sacramento County. We are including information for the other counties, but we're still communicating with all the emergency managers in that area. And the plan would be if people like the tool, we can include that in other counties. It really depends on the use of, whatever anybody wants. If this is something that can be expanded, I think it can be expanded to be useful for all situations, just not flooding situations.
Thanks. Can you talk a bit about the team expertise that was put together to develop this tool and the time it took to get it up and running?
That's a very good question. So we have a lot of very smart programmers that have produced similar tools. And one of the tools, if you go onto the internet, it's called the FODSS, and it's a flood, basically it's a flood database that was developed for the Department of Water Resources in California. That is actually on the internet. What we did was we used that as a base, and then we actually took information out of that didn't pertain to the Delta area, and just by discussions with others included all the information like critical facilities, levees, things that are important for the Delta area. So there's a number of things you can add to the tool, but we tried to just make it very specific for flood situations in the area. So that it was basically hydraulic modelers, emergency managers, and programmers that basically put the base tool together, that what is shown today.
Thanks. One other question we have here is, was the Corps of Engineers a partner organization in the development and use of this tool?
So that's a very good question. So the grant came from the state of California. It was through Sacramento County. We are using data from the Corps of Engineers, some of the programmers in our office do communicate with the Corps, but I would say that they have not been directly involved, even though we are using the data, and I believe some of them know about it. It's been more the state of California and local agencies with County of Sacramento at this point anyway.
Looks like we have time for another one. I wonder how much the grant money was to build this tool. Was there any grant money involved?
Yeah, there was grant money involved. It was I don't know if I'm to talk about how much money, but it was yes, it was a grant that was applied, and it was very specific to one area, what we call the Delta boundary. So if you go in my presentation, I talk about the legal Delta boundary, and that's where we focused on, which includes 5 counties at this point.
That's the last of the questions at this point.
Okay. All right. That was an exciting project. I really, you're always trying to improve technology and use all the data that's out there. So that's, the best available, and, updating as things update. It's all set up to be able to swap out old data with new data if it's available. So it's a fun project.
Yes, we can go to the next presentation now. It's being presented by Mark Bartlett, and he is with Stantec.
Hi, and welcome to the presentation on extreme flood mitigation by dams under present and future climate. As shown here in the background, heavy precipitation events do push dams to their limits. And the question is, how do dams perform under these heavy precipitation events for present and future climate? And more importantly, are our dams up to the challenge of handling ever more extreme events as we progress into the future? And this is important because heavy precipitation, for example, just recently caused the breaching of 2 dams in Michigan, and that resulted in significant property damage and potentially could have resulted in loss of life. And these heavy precipitation events are projected to increase in the future, and already over the past 60 years, we've observed a noticeable increase in heavy precipitation all over the country. Particularly in the Northeast, we've observed a 55% increase in heavy rain or snow, ranking among the top 1% of daily events. The status quo is that the extent to which dams mitigate flooding remains uncertain, and we can't necessarily use the distributions that apply to natural flow regimes and assume that they fit for controlled and managed flow regimes from dams. A possible way forward is to create a stochastic model of rainfall that is consistent with NOAA Atlas 14 values. This model of rainfall can then be coupled to soil moisture dynamics at a point. The soil moisture dynamics at a point can then be scaled to an entire watershed area based on an assumption for spatial heterogeneity. The watershed fluxes provide runoff to the dam, and based on dam operations, we can then calculate the discharges from the dam for the 100-year event, 500-year event, 1,000-year event, and so on. And this provides a methodology for easily assessing climate change impact on dam discharge. So to start, we'll be looking at how we link typical year values of storm rainfall to extreme values. This is how we'll be extracting our stochastic model of rainfall that's consistent with NOAA Atlas 14. This model of rainfall will be connected to a soil water balance. The soil water balance in turn will then be expanded to an entire watershed area based on assumptions for spatial heterogeneity that provide runoff, and the runoff will then be cascaded to a dam reservoir, where we can then examine reservoir dynamics and calculate return frequencies of dam discharge. We'll be looking at this approach for an application out in California, where we examined the discharges from dam for a flood study. And finally, we'll be examining how this approach is useful and amenable to understanding how future climate will impact dam operation and dam discharges. We extract our stochastic model of rainfall, by connecting typical values of rainfall for a storm event to NOAA Atlas 14 values of rainfall. To start, we first approach this problem by looking at looking at a pattern of rainfall over the course of a year. So here we're looking at rainfall events where each bar represents a lumped amount of rainfall per event. If we look at the various values of rainfall for each of these events and aggregate them into a distribution, we have the distribution at the right, shown with the histogram bars. And this distribution, this pattern, is typical of most areas around the world, and it's well described by a mixed exponential distribution, shown with the dashed dot line. The analytical form is shown here. One doesn't need to be too concerned with it, but note that this mixed exponential distribution depends on two parameters: an average value of rainfall for more extreme events, and average value of rainfall for lower, more typical events. In conjunction with this statistical description of rainfall per storm event, we also consider the description of times between storm events. So looking at the same pattern of rainfall, we consider the time between storm events, aggregate the various different values that are observed, and we arrive at the distribution shown to the right, where the probability density is shown on the y-axis and interstorm times is shown on the x-axis. Again, this pattern is quite typical of most watersheds around the world. An exponential distribution, as shown by the dashed dot line, well fits this pattern. And the analytical form of the exponential distribution is shown here. Just be concerned with the parameter lambda, which describes the frequency of storms. So the frequency of storms and the average value of rainfall, they characterize the hydroclimate of the system. And because these values are exponentially distributed, the arrival process of rainfall is called a Poisson process. And for a Poisson process, we can describe the probability of having different number of storm events over the course of a year. So here we're looking at the probability distribution for a number of storm events for the city of Wells, Nevada, which is a drier climate where the frequency of rainfall is lower. And to the right of that, we're looking at the distribution of the number of storm events for a wetter climate in Neversink, New York, where there is a much larger frequency of rainfall around 0.3. So the probability of an n number of events, in our case occurring over 365 days, is based on the frequency of rainfall, and it's described by the Poisson distribution, where the analytical form is shown here. Again, don't be too concerned about it, but just know it exists, and we're going to use this to move from our typical values of rainfall per storm event to our extreme values of rainfall for the worst storm event for any given year. Now, when we move from daily rainfall to extreme events, we're looking at the, as I mentioned before, over a block of time, 365 days. We're looking at the maximum rainfall event that occurs over that block of time. And this can be characterized statistically. So to do this, we start with the non-exceedance probability for a single event, which is the integral from negative infinity to an arbitrary value of rainfall. And we're integrating over the mixed exponential distribution that was shown previously, which is graphically shown to the right here. We then consider the non-exceedance probability for an n number of events, which is simply the non-exceedance probability for the single event multiplied an n number of times. Now, for a non-exceedance probability for a maximum event, we consider the non-exceedance probability for n multiple events, and we weight it by having an n number of events, which is the Poisson distribution. And we sum over all the possible number of events that could occur from 0 to an infinite number of events, theoretically. And when we do this, the summation converges to this nice analytical form shown below, and this is our extreme distribution of rainfall. So we move from our typical values per storm event shown above, and the black arrow shows how we've transformed to an extreme distribution of values, where we're just looking at the statistics of that maximum value of rainfall that occurs for any given year. And the average has now changed from a value of 0.37 to a value around 2.2. It's much greater, as would be expected. If we fit this analytical form of this extreme value distribution to the NOAA Atlas 14 values, we have then found a distribution, the correct form of our mixed exponential distribution that describes our typical values of rainfall for storm events. So we take this analytical form of the distribution that was previously shown, which is shown in the top left, and we fit it to the NOAA Atlas 14 values, which are shown graphically below. So in the graph below, we're looking at precipitation values on the y-axis and return period on the x-axis. The NOAA Atlas 14 values are shown with the red x's, and our analytical distribution has been fitted to these values. And when we fit our distribution to these values, we find the correct parameters for the mixed exponential distribution. We find the correct average value for the more extreme values of rainfall for the mixed exponential distribution, as well as the average value for the lower values of rainfall. And as I previously mentioned, this distribution depends on the amount of time considered, which in our case is 365 days. And it depends on the frequency of rainfall, lambda, which our case is easily derived from the meteorological record. And the distribution, as I mentioned before, this piece of R is that mixed exponential distribution for the value of rainfall for any given storm events. We then couple the stochastic model of rainfall to soil moisture at a watershed point. Our stochastic model of intermittent rainfall propagates down to our watershed point, which has vegetation. This vegetation then controls the partition of the rainfall at a point and controls the partition between runoff and infiltration into the soil. And this infiltration can eventually pass through the rooting zone of the soil to become leakage that then passes to the stream as base flow. The vegetation is a significant control on this partition. It controls the rooting depth, which controls the amount of soil water available for evapotranspiration. And in turn, this controls the decrease of soil water between storm events. between storm events, we observe the following behavior as shown from this experimental data from the Duke Forest in North Carolina, where soil moisture is shown on the left-hand axis and varies between 0, completely dry, and 1, completely saturated, and days of the year is shown on the x-axis. Rainfall is shown with the black bars, and what we notice is that for each rainfall event, there's a corresponding rapid increase in soil moisture from this experimental data. And between rainfall events, there's this corresponding decrease in soil moisture. This rapid increase in soil moisture corresponds to our model where we're showing a rapid increase in soil moisture from instantaneous pulses of rainfall, where each rainfall pulse is sampled from a mixed exponential distribution. And so our model compares quite well to this experimental data, and in general compares quite well to experimental data from other sites, and I'm happy to share more information on this after the talk. The challenge is scaling this behavior at a point to behavior over an entire watershed area. When we move from a single point to a watershed, we're looking at many different points interacting. So we have a many body problem. And then the similar problem exists in physics and statistical mechanics, where physicists are looking at a gas in a box and the different gas particles interacting and looking at how these particles interact in a phase transition to form a liquid. Instead of looking at how these various different particles interact, the approach is to look at how a particle interacts with the average state of the system. So one moves from a many-body problem to a one-body problem. And this approach has been successful in physics in capturing phase transitions. Here, we're applying this approach in watershed hydrology to represent how a point interacts with the overall watershed. In this case, the point is interacting with the average state of the watershed as given by the average water storage, unit area water storage over the watershed. So for an arbitrary watershed, when the average state of the watershed is full, the mean field assumption in this case shows a distribution of soil water where the different point values are clustered towards a state of saturation. As the average state of the watershed declines and becomes drier, this mean field approach shows a distribution where there's more dispersion, more variability in the values, the point values of soil water. So there are likely to be points that are more saturated and points that are drier as well. As the overall watershed state continues to decrease and dry down, the point values shift over and cluster around drier values. And this is how this mean field approach is implemented in watershed hydrology. There's a distribution of point values of soil moisture that shifts with the average state of the watershed. We use this approach to first upscale the point scale behavior for the runoff response. So our simple model of soil moisture at a point can be represented by a bucket of soil water that's forced by incoming rainfall. When rainfall increases soil water beyond the bucket capacity, there's a filling and spilling and a threshold excess runoff mechanism at a point. However, for points that are near the stream, there also is transmission of rainfall to the stream through a pre-threshold runoff mechanism. For example, through macropores that exist in the watershed and riparian areas. We take this point scale behavior and we upscale it to the entire watershed based on the mean field assumption. We're integrating over a distribution of soil water variability, and in this case also a spatial variability of rainfall. And we're integrating over different assumptions for the spatial variability of soil water that are specific to different models that are readily used. So the runoff distribution, again, is the point scale behavior integrated over the spatial variability based on the mean field assumption. And the SCS curve number method has its own unique assumption for soil water capacity and the distribution of soil water based on the mean average value of the watershed. the variable infiltration capacity and probability distributed model have another unique assumption for the variability of soil water based on the average state of the watershed. And top model, topographic watershed model, have a different unique assumption for the variability of soil water based on the average state of the watershed. Based on this, we can find the runoff distribution for these various models. And when we take this distribution and calculate the average runoff, which is a rainfall runoff curve, has the same form significantly for all the various models. And runoff, the rainfall runoff curve is simply rainfall multiplied by the fraction of area that is saturated, plus rainfall multiplied by the complementary fraction of area that is not saturated, but where there is a transmission of rainfall to the stream based on this pre-threshold runoff index. And this is representative of riparian areas that are closer to the stream. This approach allows us to look at how all the different models compare to data. For example, we're looking at the Davidson River watershed and rainfall runoff values where each gray dot represents a rainfall runoff event. We can rank order these events to create a rainfall runoff curve as shown with the red dashed line. And we move from the left panel to the right panel, the red dashed line becomes the gray dots. And we now see how the various models compare to the data. In this case, the SCS curve number method with the long dashed lines compares less well, and the variable infiltration capacity in top model better describe the rainfall runoff response of the Davidson River watershed. In many cases, it may be worth not using the curve number method and looking at how different rainfall runoff curves or models represent the runoff response for a watershed and the corresponding flooding. We take the same approach that we took for upscaling the runoff response to the point, which resulted in our soil water increasing because of rainfall as given by our stochastic model of rainfall and decreasing because of the runoff curve. We use the same approach to upscale interstorm behavior at a point. So we have our simple bucket of soil water at a point. We upscaled it based on the mean field assumption to get the runoff curve response. And now we're considering interstorm behavior, so we consider evapotranspiration and leakage to the stream. We upscale these behaviors, and we move from the functional behavior at a point, which is this function f, dependent on soil water at a point, and we move to f bar and x bar, which describe the average behavior over the watershed. And the reason why we have to upscale in this way is because we can't simply take behavior at a point and plug in the average value. That's not going to represent the watershed. We have to find the average of the function. That represents the watershed. And this equation is a stochastic differential equation because the change in average soil water for the watershed over time depends on rainfall, which is driven by the stochastic model of rainfall that was described previously. We then couple this watershed behavior to the dynamics of water in the reservoir behind the dam. This then allows us to quantify dam discharges. So we have our stochastic model of rainfall, where each rainfall event has an amount of rainfall that's described by a mixed exponential distribution. This feeds into our upscaled watershed water balance, where water content for the watershed increases because of rainfall, decreases because of evapotranspiration, decreases because of base flow, and decreases because of runoff. In turn, base flow and runoff cascade into the reservoir of the dam, and the volume of water in the reservoir of the dam increases because of base flow, increases because of runoff, decreases because of discharges from the dam outlet, and also decreases because of discharges from the dam spillway. So these two simple equations in our stochastic model of rainfall capture the entire process of the system. And to capture dam discharges, we model 30, 40,000 years of rainfall and cascade the rainfall values through the system. and then calculate the corresponding dam discharges based on the functions in the yellow box. We then use this approach for various watersheds that we're studying to understand the return frequencies of dam discharge. So what's the 100-year event flow from the dam? What's the 500-year event flow, for example? And I'm now going to show this approach and how we applied it to a study area in Merced, California. So in Merced, California, riverine flooding is controlled by Bear Creek, and Bear Creek is regulated by Burns Dam and Bear Dam. These are the two dams that we studied for a client that examines flood risk around the country. For our model, we had to make a few simple assumptions. We assumed evapotranspiration varies linearly with the water content of the watershed. Similarly, we assumed that base flow also varied linearly with the water content of the watershed, and this linear relationship is shown to the graph on the right. Spatial heterogeneity in runoff was based on the NRCS curve number method that is shown on the graph to the right and below, where we have runoff and rainfall runoff. We have rainfall runoff curves that vary with the water content of the watershed based on a max potential retention. Soil depth and vegetation, evapotranspiration were based on a Ameriflux site at Tonzi Ranch, California, and the California Irrigation Management System was used to scale these values to the Merced location. Dam operation was based on the Army Corps Operations Manual. Our stochastic model was taken from the NOAA Atlas 14 values. So we took our extreme value distribution, we fit it to NOAA Atlas 14. That then provided us with a mixed exponential distribution of rainfall amounts per storm event that was consistent with NOAA Atlas 14. This mixed exponential distribution of rainfall amounts was then used to force the model. Dam discharges, as mentioned, were based on the Army Corps of Engineers Operations Manual. The values here for Bear Creek and also for Burns Creek were linearized. Here we're seeing the values for Bear Creek with the dashed line. The linearized version is shown with the solid line. We see discharges from the dam outlet for volumes below 8,000 acre feet, and discharges from the dam spillway occur for volumes greater than 8,000 acre feet. For this approach, you generate 40, 50,000 years of rainfall and then propagate through the watershed system, and then in turn propagate runoff values from the watershed system into the reservoir system. So for each year, we have a variability of soil water over the rainy season, which is about 200 days, and we have this corresponding variability in reservoir volume over the same 200 days. Now for each year, we take the maximum volume of water in the reservoir, and we take the maximum value for each year and aggregate those values into a distribution. So here we're looking at an annual maximum distribution of volume of water in the reservoir, and it's bimodal. It has a first mode, which describes the case where the volume of water is below the spillway of the dam, and the second mode to the right describes the case where the volume of water is above the crest of the dam spillway. This distribution, this annual maximum distribution of the volume of water in the dam, is transformed into a corresponding distribution for the discharges of flow from the dam based on the previous Army Corps relationships that were presented. And again, it's a bimodal distribution. And this bimodal distribution shows why the typical unimodal distributions that are applied to describe the statistics of natural flow don't necessarily apply to manage flow regimes from dams. We can then take this distribution of discharges and convert them into a return frequency curve for dam discharge. So here we're looking at the return frequency curve for the different dam discharge values as a function of storm return period in years. We're looking at the frequency curve for Bear Creek Dam on the left and for Burns Creek Dam on the right. And this approach of generating 40, 50,000 years of values and propagating these values of rainfall through the system doesn't take very long. This approach is quite efficient. Generating these values and generating these graphs took all of about 10 minutes. And in addition, when we first did the study, we didn't realize that there were gauge measurements taken by the Army Corps at each dam outlet. After the study, I took this data and processed it to place it on the graph here. And as we can see, these values compare quite well to the values on the graph, which shows the value of using a simple model with very few parameters. We can also use this approach to understand how dams will operate under future climate regimes. And this is important to consider because in many areas of the country, there will be an increase in heavy precipitation. And here we're looking at the increases in heavy precipitation over the United States, where the dark blue indicates a 40% increase. And for Merced, the area that we're looking at in particular, we're observing around a 35% increase in heavy precipitation rainfall events. So what we can do is we have our mixed exponential distribution of rainfall, which is consistent with NOAA Atlas 14 values. And as you may recall, that mixed exponential distribution has an exponential distribution for smaller rainfall values and an exponential distribution for larger rainfall values. The two are mixed together. What we can do here is we can take the distribution representing the larger values and we increase the average of that distribution by 35%. In the end, because we're just increasing these larger, more extreme values, these heavier precipitation events, these 1% of heaviest events occurring on a yearly basis, we end up with the same average annual rainfall because we're just increasing the maximum. But we have a significant change in the return frequency curve. And as shown here, the 50-year event in the future is the 100-year event currently in the present now. And the 100-year event in the future, the 100-year discharge in the future from the dam, is currently the 500-year event now. So this approach provides a way of planning for what would be expected in a dam in the future and how the dam is going to mitigate a 100-year event in the future, which currently is the 500-year event. So in summary, for rainfall, we went over a simple theory that linked typical years, everyday values of rainfall to extreme values from NOAA Atlas 14. This is a fit-for-purpose framework. It's relatively simple. It's very efficient, quite fast. I ran 40,000 years of simulations in about 5-10 minutes. And it captures the cascade of rainfall into the reservoir and out of the dam. The approach provides a method for calculating flooding extremes, doesn't require the use of gauge data, and it provides an easier analysis of extreme event statistics, and it's a possible path towards understanding flood risk driven by climate change. And with that, I'm happy to take any questions.
Hello, everyone. This ends the portion for this session. We are now going into the question and answer portion. We only have 2 questions at this point in time. If anybody has a question, please enter it into the Q&A so that we can ask Mark. Mark, first question. How widely can the mean field assumption of soil water vary? And is it estimated based on factors like vegetation, slope aspect, and angle? How does it relate to AMC or CN calcs? If it varies, what size area can you composite it across?
So I would say it could vary quite widely depending on the region of the country one is looking at. The original SCS curve was based on a series of experimental watersheds across the country. Many of them were agricultural watersheds, and that's how the curve number equation came about. It has an underlying assumption for the variability of soil moisture. And now that assumption's applied to pretty much everywhere in the country. So I would say one future area of investigation would be linking the type of mean field assumption and the resulting model to factors such as vegetation and slope angle aspects. and other factors that are relevant. And for the AMC2 condition for the CN calcs, if you take that mean field assumption, then you compose that stochastic differential equation that I showed. You force the precipitation through that equation, you're going to get a series of soil moisture values. If you aggregate and bin all those values to create a distribution, you could take the average of that distribution, and that would be your AMC type 2 value. And or you could consider the 10th percentile, the 90th percentile, and those could be your AMC type 1 and 3 conditions. And I would say, in terms of what size area this can be used for, I'd say it could be used for an area where probably up to like a Huck 12 size. You don't want to go too large because this assumption also follows. You could relate the size it applies to, say, to the size that the SCS curve currently is recommended to apply to. As you get too large, then you have to make further assumptions for this. You could make it larger. You just have to make assumptions for the variability of rainfall, accounting for areas that aren't receiving rainfall and areas that are. But it could be done. It just, as you scale it up, you have to make sure that your assumptions are commensurate with the scale that's being examined. And then for the number of years that were being used, we ran about 40, 50,000 years of rainfall through the model. Let's see. The modeling of rainfall under climate scenarios. So I'd say the major challenges are usually it's understanding the evapotranspiration in this case, and the average soil depth and vegetation type for an area. As the rainfall itself is just being extracted from NOAA Atlas 14, so that exists for many areas of the country. And because this approach is relatively simple, I mean, I wrote the little code that did this program in about 2 weeks, and running it doesn't require much resource at all. So it could be used for less resource communities to understand how their dams will mitigate flooding downstream in the future.
Another question there would be, how can this technique help predict probability of dam failure due to extreme events over some period of time, or can it?
Oh, let's try to find where that question is. Okay, I see it. Well, we require coupling it to another modeling approach. So right now we have the amount of water behind in the reservoir and the discharge through the dam. So it could be done maybe similar to how levee failure is done, where you have a likelihood of failure curve based on different conditions. That would have to be investigated further, but I would say this approach is amenable to taking it to that step.
Thank you. Another question. How did you calculate the precip climate scenario? Was it RCP 8.5? Sorry, missed this part of the methodology. Or did you use the percent increase from the PAT?
Let's see. I'll go back a slide. I took the climate scenario from noaaclimate.gov, and the data was NCA4, so it's the published. I'd have to the emission scenario was a higher one. Now the coding for that I'd have to look into that, but it was the higher. Usually there's a lower trajectory, a middle one, and a higher. This was the higher one. If that's RCP 8.0, I think it was actually.
Mark, are you going to, I lost it, somebody added another question. Where did it go? how many simulation runs were done to account for the stochastic nature of the rainfall model?
I did 30 to 40,000 years of simulations. And so for each year, precipitation arrived according to a Poisson process. So the way that's done is you just generate a random number between 0 and 1, and you compare it to the frequency of rainfall. And if it's above a certain threshold, one has a rainfall event. If it's below a certain threshold, one doesn't have a rainfall event. But on average, the number of events per year was commensurate with the number of events per year that is observed in the meteorological record. So that was done for 30 or 40,000 years to then pick off the most extreme events from the dam. And then I think another question was, how do you generate those rainfall values? So the way it's done is you have to generate the time of the rainfall events, as I mentioned previously. So you generate a random number between 0 and 1, and you see if it's below a threshold or above a threshold. And depending on that threshold, you either have an event or don't have an event. And when you do that, the events, because we're working with the Poisson process, the time between events is exponentially distributed. So you just generate rolling dice, essentially, number between 0 and 1, generating if an event occurs. And if an event does occur, you again throw the dice again, you generate a random number between 0 and 1, and then based on that number between 0 and 1, you draw a number from that mixed exponential distribution, which is the rainfall amount. So you end up generating a time series like the time series I showed earlier in the presentation, and we did that over 30, 40,000 years.
Interesting. There is one more question here. It says, so could you use a similar process for other infrastructure such as levees?
Yeah, potentially, yeah. I would say this process is amenable to looking at levees. I've used it to look at stormwater basins, for example, in green infrastructure. So it has a wide range of applications, I'd say. I also saw there's a question about NOAA Atlas 14 data being outdated. And yeah, it's true. It's based on 50, 60, 100 years of record in the past. And so one challenge or one way going to updating is using climate models. For example, you can look at how the precipitation from the climate model has predicted at the present changes in the future, and you can look at precipitation over various quantiles, 0 to 100, see how those quantiles have changed. So the 50th quantile event has increased by a factor of, let's say, 1.3. So you then could take that 1.3 factor and apply it to the precipitation you're measuring on the ground, for example. That would give you a new form of that mixed exponential distribution. You run that through that formulation I showed for mapping that mixed exponential distribution to an extreme value distribution. So that would give you a new distribution of that is commensurate with NOAA Atlas 14. And the way I would then use NOAA Atlas 14 is I would make sure that the tails of the distribution from NOAA Atlas 14 are I would use that, make sure that same tail behavior is then captured in my new distribution. So it's a way of kind of combining GCM output, data from gauges on the ground, and NOAA Atlas 14 to bring them into the future.
Another question that we have on here is, how did you overcome the evaporative issue? Evaporative.
Oh, so the evaporation between events. So when I ran the simulation, as I mentioned, I was throwing the dice to generate when an event occurs and how much occurs. When an event wasn't occurring, evapotranspiration was drawing down water in the watershed based on a linear relationship where we simply had a maximum evapotranspiration multiplied by the soil water content of the watershed normalized by an overall storage. And that works fairly well. I've worked in making models of evapotranspiration for different plant types, and usually when you aggregate over a larger area, that linear relationship works quite well. So you're going to have a fast drawdown when the soil water over the watershed is quite high, and that's going to taper off as the watershed water content declines.
One other question. Do you think regional subsurface flow, loss of water to deep aquifers, could have an impact on soil water content?
Yeah, that's a significant component of this. When we're looking at Merced, there isn't too much flow to the aquifer because of the climate it is in, but that can be a significant component. I would say the way I went about for Merced was I took when I ran those simulations, I calculated an average value of soil water. And that gave me multiplied by and from that I was able to calculate an average value of evapotranspiration.
Yeah.
So based on that, you can map where the model behavior is falling on the Buteyko curve, which describes a partitioning of rainwater between evaporative losses and baseflow and runoff. And in this case, it matched quite well. I'd say in other watersheds, that would be a potential way of calibrating the subsurface flows to groundwater, making sure that the model behavior falls close to the Buteyko curve where it should be.
Thanks, Mark. That was very informative. We're going to wrap this session up. That was the end of the questions that we had and the time. Hope everybody continues to have a good conference and stay safe and healthy. Thanks.